Fair enough. Now that we've talked about electrolytes and solubility, we're going to talk about a specific kind of reaction, which is an exchange reaction. Ions changing partners. There's two kinds of reactions that fall under that category. One of them is a precipitation reaction between ions that are positive and negative. You're experts in positive and negative ions. Now we're going to find out what happens when different ions are introduced to each other and maybe they precipitate, not dissolving in water, or they stay dissolved. Let's go to work. Well, hi everybody. Hi, Mike all up in this. Going to talk to you about precipitation reactions today. Precipitation reactions are a form of what we call exchange reactions. So it's basically you have two things that get dissolved and become dissolved in water, and they're cation and anion, and they flip partners. This is kind of what happened to me at prom when I was a senior in high school, but I don't think it'd really be very professional for me to talk more about that. So, but you got cation 1 with anion 1 goes, and for some reason those cations and anions rearrange themselves, and in this case we're going to talk about how, according to the solubility rules, they make a precipitate. And so that's the driving force of the reactions we'll talk about today. Now look, there's all sorts of things, they call them double replacement, single replacement. But look, the way I look at things, it's not really our job to give things fancy names. What we want to be able to do is predict the outcome of one of these kinds of reactions. So I'm not going to get into all the naming of different kinds of precipitation reactions or exchange reactions. There's basically three kinds of reactions. So the two that we're going to talk about today and the next time are precipitation reactions and acid-base reactions. Those have the form of an exchange reaction. So let's get into it and let's talk about something specific, and then grab some solubility rules while we chat today. All right? So let's say we had a reason to want to predict the outcome of that reaction right there. And you will notice that I have written beside, I have molecular and then I have ionic below it, because these things are much easier to predict if you put them in the ionic form. So what I'm going to do is I'm going to say, all right, first of all, you notice I didn't put anything right here? I didn't put anything here yet because I got to look it up. Is that a solid? Is that something that dissolves in water? So, spoiler alert, they're both going to dissolve in water, because if you go ahead and get your solubility rules out, you'll notice nitrates, anything you pair with nitrate is soluble. And so, therefore, this lead nitrate, I'm going to go ahead and throw an AQ in there. All right? And then I've got iodide here, and insoluble exceptions or combinations that aren't soluble would be silver, mercury, and lead. But potassium, everything with potassium is always soluble. So you've got two things pointing to the fact that that's going to be an AQ up in there. All right. Now, what I'm going to do to make things, well, because usually they'll say, hey, what's the ionic form of this? And you have to do it. But just because I want to show you how much easier it is to see what's going to happen when I go and put this in the ionic form. Now, how did I know that was a Pb2+? Because I know that from the solubility rules table, nitrates are -1 each. So that nitrate, -1, paired twice with a lead, that points to the fact that lead must be lead 2+. And so now here's the thing that happens. This particular formula, when it hits water, it breaks into 3 pieces. And that's because there's 2 nitrates and 1 lead. And so this is kind of like what we were talking about taking the ion charges and making the formula. Now we're going backwards because these things are breaking apart when they hit water, and the 2 comes out front and is a coefficient. That's very important to realize the difference. That means that when this breaks into its ions, it is going to be 2 nitrates. Fair enough? Let's look at what's going on here. Potassium iodide. Now you could just remember your rules from the periodic table that potassium always makes a +1. And iodide being in group 7, 7 minus 8, or you just look in your solubility table chart, you know, it's sitting there, I minus. Now, it is easier to determine what's going to happen here. Are any of these new pairs of ions going to interact with each other? And by interact, I mean make an insoluble combination. So we had these in separate containers. Let's use our little imagination here. This was a test tube that had this in there, and you had a separate test tube that had that in there, and now you're going to add them together, and now the lead ions are now suddenly able to be in contact with the iodide ions, and the potassium ions are now in contact with the nitrates. And so the question is anything going to happen? So let's do the first part. Lead and iodide. Hey, right there. Lead is an insoluble combination with iodide. Now there's a problem going on here. Can you see what that is? I can't combine a lead 2+ with a I-. There's no PBI. It could be PBI2. So what do I do now? Do I just give up and go home and play World of Warcraft all night and you know, sit on the couch? No, we don't do that. So we're gonna go ahead and do this. Can I do this? You bet I can. And I found out that now that's going to ripple through, and there's going to be a 2 there, and there's a 2 there. And so what the product is going to be, one of them is going to be PBI2. So now we're going to go back to like our old thinking and putting ions back together to make a formula of an ionic compound. And because that's an insoluble combination, an S goes right there. That isn't it. And then actually you don't break this up into its ions, even though it's the ionic form, because the only things that break into ions, electrolytes, are soluble ionic compounds. That is insoluble. So this goes P up there too. They're in the same form. So let that sink in there. When you have an insoluble combination, they're not AQ anymore. You only see AQs where things dissolve in water. So what's going to happen to the other leftovers? Once in a very rare instance, they will precipitate with each other too. But if you go look at the solubility rules, you got 2 things pointing to no. K+ is insoluble with nothing. NO3- is insoluble with nothing. And so this is going to just stay the same form on the right. So when I write this here, I'm going to go ahead and I'm going to say plus 2K plus aqueous plus 2I minus aqueous. Oh my goodness. NO3-. I Freudian slipped. 2 NO3- aqueous. Now in the molecular form this would appear this way. And remember, the molecular form is the less truthful form that is sort of shorter. 2K NO3 aqueous. So our molecular form and our ionic form are both all done. Now let's talk about what happens next. Sometimes they ask for something called the net ionic form. what's the net ionic form? That is where you just show only what is changing. So let's kind of recap. Molecular form is when you had the formula put together and the cations are combined with the anions, even if they're dissolved. That's just kind of a shortcut. Ionic is the more lengthy version of writing it, where all the ions that are AQ, not the ones that are solid, but the ones that say IQ, are busted up into their respective ions that are free. Net ionic is where we do this. If something appears on both sides in the same form, we, sort of like in algebra, we cancel it. These things are what we call spectator ions. And it's not like they're not there. They are there. It's not like they're not important either, because basically every positive's got to have a negative. I can't put lead into water and dissolve it without it being paired with something soluble. It's just that they're not having an active role in the chemical change of producing a precipitate. So we cancel them out in the ionic, and then the net ionic sort of shows you the driving force of the reaction, which is that whenever a lead sees two I minuses in solution, they're going to precipitate. It doesn't matter where the lead came from. It doesn't matter if that was lead nitrate or lead chlorate or perchlorate or acetate. It's going to make a precipitate. Whenever you have a soluble form of lead with a soluble form of iodide, you get lead iodide. And so there you go. That is the three forms of any reaction that we will keep talking about. And so the only thing left to do is to practice it a whole bunch more, and by whole bunch I mean probably I will not make you nauseated if I just do two more. So let's do another one where we write all three forms of a precipitation reaction. Here we go again. So what we got is we've got two compounds, which you can go verify for yourself. I have every right to throw AQ in there because everything sodium dissolves with anything negative and anything nitrate. So that is sodium carbonate and calcium nitrate. So the first thing to do is to see if we have any insoluble combinations, and the easy way to do that is to bust it up into its respective ions. So underneath the word ionic, I'm going to go ahead and write 2Na+. See how that 2 came out to the left? And then CO3 2-. Remember, you could always go and look in your solubility chart and find out that a CO3 is a 2-. But the charges of these things is what kind of bails you out. And so now what we're going to do is we're going to do that with the calcium nitrate. What's that make? Well, you know that the stable ion of calcium is a 2+. And then you have 2 NO3-. Hey, look, we got the same sort of thing going on, because NO3- are usually things that pop up and they don't end up precipitating. I know I might have spoiled all the suspense there. And now we're going to go look to our solubility chart and say, hey, does a sodium precipitate with a nitrate? Well, you know, nitrates dissolve with everything. But does a calcium make an insoluble combo with a carbonate? Now here's the thing. If you remember, carbonates are down here. Carbonates are part of these insoluble negative ions that usually don't dissolve. And so you say, hey, group 1, sodium, that's why it dissolved in the first place, but it ain't going to dissolve. Calcium is not an exception to being insoluble, which means that calcium and carbonate make an insoluble combination. And if you remember last time, I put an eggshell in water, and eggshells are largely made of calcium carbonate. And so what we're going to do now is we're going to slap them together and write that formula in the correct fashion with the metal on the left and the non-metal on the right. And so it's going to be CaCO3 solid. Both down there and up here in both the molecular form. I almost wrote an AQ there. So now what's going to happen to the leftovers? They're going to be spectator ions, so I'll include them just the way they are, Na plus and 2NO3 minus. If you wanted to write that in the shorter form, that is a 2NaNO3 aqueous. There is the molecular and the ionic forms of that reaction, and now what we can do gives you a big feeling of power, right? We're going to go and cancel all the spectators. You can make whatever sound effect you like, but I like the whew. So then what you could do is now rewrite this without the spectator ions. That's the net ionic, is that whenever a calcium and a carbonate see each other and come into contact, the driving force of this reaction is that they will make a precipitate. And you know what? We got lucky this time. Everything, I don't know why I keep thinking AQ, everything balanced. As a matter of fact, you know, in that last one we had to throw a coefficient in there. If you ever need to check yourself before you wreck yourself, make sure that each side of the equation has equal number of positives and negatives. And here we had a 2 plus, and then we had 2 plus and two negative ones. And so that had a charge of 0. This has a charge of 0. And that'll be a way to know that you balanced it correctly. So, okay, I'm going to give you a little bit of a heads up here. This next one's going to be a weird one. Hang in there. Almost done. I promised something weird, and here it comes. We're going to go through the same procedure here, and we're going to go ahead, and that's the molecular form, and we're going to bust these electrolytes up into their respective ions. So that would be a K plus, and that would be a Cl minus. Single atomic ions that you know from the periodic table. That's a calcium, that's called chlorate, ClO3 minus, and you'll notice that everything with chlorate, it's kind of like a nitrate. So they're very often spectator ions, but you could tell since that it's a -1, and you know that a calcium being in group 2 is a +2. And we go through the same procedure here. That 2 would come out in front, ClO3 minus. And then we go to our solubility rules chart. And we say, oh, there's chloride. What's insoluble with chloride? Silver, mercury, lead. And now chloride's just coming into contact with that calcium. So does calcium make an insoluble combination with chloride? Nope. They gonna not precipitate. Okay, well then must be that a potassium and a chlorate make an insoluble combination. Well, potassium's soluble with everything, and so is chlorate. So what gives? What happens? And the answer is, what happens here is what we call in science nothing. Nothing happens. These two get to swim in solution happily with each other, and they don't make any insoluble combination, so there is a big old no reaction. So it's not a foregone conclusion that every time you put different ions together, you get a precipitate. In this case, you'd have a colorless solution mixing with another colorless solution, and you'd have just another colorless solution, and you'd have more ions in there that you can't see because they don't have a color, but that'd be a big old no reaction. So we kind of faked you out there. See how it was weird? But not really. We didn't fake you out because you have this tool, the solubility chart, telling you what precipitates with what. And the nice thing is, you know, most of the time these things, if you've done a few of them, you've done them all. The only things that change are, you know, who the cast of characters are. And so go try some more. It's kind of like balancing reactions. Go and see if you can go find some homework problems in the back of the book or on your online homework or wherever. Just go find some more practice and you will get good at these little tricks that are hiding, like the first one where we had to go and balance it. And you know that, like with the lead iodide, you knew it had to be a 2-to-1 ratio because we drilled that so hard several lessons ago. So, all right, next time something similar. We take an acid and a base, and they don't make a precipitate, they make water. That's me foreshadowing the next lesson of acid-base reactions. Till then, see ya, toodaloo, bye.